Okay, hi guys. Welcome to the fourth PyData meetup. It's been a while, but we're glad to be back here. Today we have a talk by Mr. Sergio. He'll be talking about enhancing vector search performance on a limited memory edge devices. So Sergio is a computer scientist with a strong interest in tackling complex problems. His expertise spans from high performance computing to computer vision, computer optimization, and edge devices. Recently, he has completed his MSc in data science at the University of West Indies St. Augustine campus. Is currently honing his skills in advanced computational techniques and driven data solutions. So before we hand over to Sergio, I'll just like to remind everyone about the PyDataTT code of conduct, right? So please be kind to others, do not insult or put down others, behave professionally. Remember that harassment and sexist, racist, or exclusionary jokes are not appropriate for non-focus or PyDataTT in any way. All communication should be appropriate for professional audience, including people of many different backgrounds. Sexual language and imagery is not appropriate. PyData is dedicated to providing a harassment-free community for everyone, regardless of gender, sexual orientation, gender identity, expression, disability, physical appearance, body size, race, or religion. We do not tolerate harassment of community members in any form and of any kind. Thank you for helping us make this a welcoming and friendly community for all. Okay, so Sergio, when you're ready, you can take it away.
Okay, great. All right. So I'll just begin. So as the title says, title of my talk today is Vector Search Performance Enhancements on Limited Memory Edge Devices. And you'll see me kind of looking for a little bit. That's just because my slides are on another screen. So I'm just gonna tilt over a little bit from time to time. Okay. So actually, right before we started, one of the members of the audience here actually had a really good question. So what is a limited memory edge device? Right. So I'll just answer that. When you say a limited memory, more devices are technically limited by memory, but specifically we're talking about devices that do not have what I would call um, uh, high access to large amounts of. So, for instance, we're talking about devices that like maybe have at most 1 gig of memory available, 2 gigs, etc., etc. And the reason that's important is because usually vector search happens on much higher memory, in much higher memory environments, which we'll talk about as we go through. Okay, so first thing we're going to talk about, what is vector search? So this is not really something I think, well, I think if you do data science, you'll probably be fairly familiar with this, but if not, maybe this will be the first time you're hearing it. But vector search essentially just encompasses creating vector embeddings, which are essentially, you think of them as this long list of numbers, but these lists of numbers essentially are related to each other with some semantic meaning. All that means is that if I have two words or two images or two words, images, songs, etc., I use a specific vector embedding technique. I can generate multiple lists of numbers, and that list of numbers will essentially be close, quote unquote, to other things that are similar to it within some vector space. And I have like a visualization demo that we'll go through later in the presentation to hopefully get that point across a little bit. But the idea is essentially we can take some form of complex data, some complex information, and convert it into a form that's essentially a numerical representation that we can then search for similar items to each item in that space. So it's two main forms: vector embedding generation and semantic search. So semantic search is the actual process of taking in a new piece of information, generating a vector embedding for it, and then searching a preset database of vector embeddings for the most similar items to your input query. Right now, the actual vector embedding generation process is a whole different problem. I will not be tackling that in this talk. We're specifically going to be focusing on semantic search, and we're just going to assume that the vector embedding generation techniques that we're using will work for whatever situation we need them to use. Okay. So challenges and objectives. So the main challenge that we have one of the main challenges we have with vector search is that vector search typically relies on very large memory devices. So really large memory, lots of computational resources. And the reason we need a lot of memory is typically because whenever you're doing vector search, you usually bring the entire vector store, or at least like a big chunk of it, into memory and search there. Like you actually load everything into memory and search right there. That's usually what we call in-memory vector search, which is the industry standard. Right? This is very fast. It's very fast, and it works because usually you need this to be like kind of on the fly. Like it has to happen really, really quickly. But unless you have a lot of memory to work with, this is not really feasible. And and if you have like an edge device which has very, very limited resources, then you have to essentially work around the fact that, well, it then becomes unfeasible to have vector search run in that environment. So the main objective of this project was to develop and assess a self-contained proof of concept vector search system for low resource edge devices. Now, just to kind of paint a picture of why this is necessary, we're going to look at some existing vector search libraries. So one of the big ones that's really well-known industry standard is FICE. It's Facebook AI similarity search, and well, it's still FICE even though they're meta now. And its strength side is like really high performance, supports GPU acceleration. It's really good for like billion scale similarity search. But the obvious limitations that will come with that, it requires GPUs. It has it requires very high resource environments, so it's just not suitable for edge devices. Some other options, there are many options. So we're only going to list 3 here. There are quite a few others, right? We have SCAN, which is optimized for high accuracy, efficiency, and large-scale data sets, and you can integrate it in really nicely with something like TensorFlow. But again, it requires significant memory and computational resources for performance. We also have something FLAN. So FLAN is just a simple FLAN is just a simple library that you can use to do approximate nearest neighbor search pretty easily. This one is one you could probably use on like an edge device, but it suffers really badly whenever you start to get into anything that's even remotely high dimension. Right? So it'll work really well for up to like 10, 15 dimensions. But the moment you start to go past that point, your performance starts to degrade very quickly. So our goal with this research was essentially to create a system that can handle large dimensional data on edge devices which have very little memory resources. Give me 1 second. Oh, my slides are not in order. So I'm just going to jump here. Yeah, so I'll jump. So why would you want to do this? Well, the main reason is because you get reduced latency that can enhance privacy. Those are the 2 main points I want to drive. If you have reduced latency, you can essentially make real-time decisions on the fly, which is really nice. And you essentially can keep all the data localized to the device that you're working. So typically, whenever you have any type of vector search taking place, the data has to go off of your device to some cloud server somewhere else, and that's obviously a breach of privacy there. And because of that travel that has to take place, you can't really have real-time applications work unless you have very good networking access and you're really close to the server that you're with. Right? So some potential applications, we have things like autonomous vehicles, we can have portable healthcare devices, we can have like rapid image analysis and diagnosis. We can have smart security cameras, drones, even integrate this into something like augmented reality glasses, and general IoT devices. Now, the idea is that this will be like a backbone component that is added alongside other machine learning techniques, right? So, like for instance, if you want to do something with like smart glasses, you would have a computer vision model that will be able to identify, that will be able to do something like object detection, take that object, convert it into a vector, and then and then do a quick search through a vector database to determine what that is really, really quickly. So it makes things really fast, really efficient. So here we're just going to talk really briefly about the system overview we actually made, right? So we're going to talk about the system overview here, and we're going to actually go into some technical details after. Then we'll go through a small demo just to kind of show how this works. Again, if you are familiar with vector search and vector databases, this may not be too exciting, but the idea is that we're doing it with very little resources, very few resources. Okay, so general overview of our system. We made our system up of 4 modules. There's an indexing module, a storage module, a database module. There's a Python API just for general information. The indexing module is where most of our work went in. And here is where we're going to manage searches for embedding, manage the actual searching for vectors within a vector database. And to accomplish this, we didn't build out a brand new search algorithm. We actually optimized, well, I wouldn't say optimized, we modified an existing one so it can be utilized on edge environments. Specifically, we took the span algorithm from Microsoft's SP-tag library. That just stands for space partition tree and graph, because it allowed us to essentially minimize our memory footprint as much as possible while maintaining a decent latency, right? We have a storage module, which is responsible for the actual storage of raw media. So in the case of like text, images, etc., it would be stored. All of that would be stored and managed by the storage module. So you would actually store the vectors and the actual data separately. And when you receive the vector that corresponds to a specific piece of information, you go to the storage module and you fetch the corresponding piece of data. We have a database module, which is just responsible for the general management of the system. So that's just pretty much boring software that just keeps everything together, manages the metadata behind the scenes and everything. And then a Python API, whose purpose is just so that you can actually utilize it. If you're a data scientist, machine learning engineer, you can actually use this to do something. So some key features is that we wanted to maintain a self-contained design. So this can operate independently without requiring any external connections, which is really important for the use case that we were pointing out earlier. So all data is stored locally, so you can maximize privacy and device compatibility. This should be able to run on any device that supports like C++ 17. Now that's and also this is optimized for ARM-based devices like the NVIDIA Jetson. Now that's kind of a big deal. That last point, that is optimized for ARM-based devices, because most vector search libraries, especially the high-performing ones, are optimized only for Intel chipsets, which makes it very difficult to utilize them on any type of edge environment. So this was a really important point we need to get across here. Okay, now we're gonna go into the actual indexing module a little bit more. This is where a lot of took place. So we utilized the library called span. And well, originally I was gonna wait to go through the entire presentation before explaining for this, but I think we'll look at the demo right after this point, because I think it'll enhance the explanation of it. So we'll go back and forth. Okay. So span essentially is an indexing techniques put forward by Microsoft via the SP-tag library that allows us to utilize minimal memory while doing vector search. It essentially has a 2-pronged approach to vector search. It utilizes a space partitioning tree and then a graph-based search at a lower level. So the idea is that your data set is first divided into small clusters via the space partitioning tree, and then it's further divided, and within those clusters, build some other data structures that we can actually use to do a fine-grained search. The actual tree structure can either be a KD tree or a branched k-means tree. This usually means that we actually have to have the data set present ahead of time, so you can't dynamically add data to the can't dynamically add data to the data set and have it automatically update. You have to have the entire data set ready, and then you do the index construction, which will take a long time. It can take a pretty decent amount of time, depending on how big the index is, how big the data set is. But after it's done, you can actually do your search really quickly every time. Now, looking at the diagram that we have on the left here, each one of those large circles essentially represents one cluster within our data set, right? And the idea is that the cluster centroids of each of those are the only things we actually store in memory prior to doing our fine-grained search. So those are the only things we have to keep in memory. And then after we have identified, so you get a query vector. After we've identified which cluster it's closest to, we then say, okay, we're going to navigate down to that cluster, and then we are going to load that partition into memory with a fine-grained search. And this fine-grained search can actually utilize things like, is usually done using things like k-nearest neighbor route. Okay. So, and well, the neat thing here is because we only ever load the data that we need at the time we need it. So we only load up a specific partition of the data set at the time of our search. We actually keep our memory footprint really, really low. Right? So I'm gonna shift across right here. So this is a quick, like a really simple thing I did earlier today, just to kind of show what vector search is, as well as like how it can be, how it works, and to also show some of the performance metrics we got in real time. So I am really hoping this does not break, because it did not break this afternoon. I had to kind of compile everything. So you guys, cross your fingers, break me. Okay. So this is all vector search on edge devices. We're just going to use some text data, and we're essentially just going to generate some 384 dimensional embeddings using this all mini LA. Right? So this is what our vector space looks like. Hopefully you can see that. And each one of these points here, each one of these data points represents one piece of text in our system. Right? And the idea is we're going to enter some query, and we're going to do a search for a piece of text. I will get, in this case, will be the 3 nearest neighbors to this text. Now, in an actual practical setting, this data set will be very, very big. For our testing, we actually use the data set of size 1 billion with 960 dimensions. But for the purposes of demonstration, we're using a very small data set with 384 dimensions, and we'll just like see how it performs. So this right here is where we can do our search. So here we're actually just entering this query here. So this will be converted into our vector, and we do a search on it. So we ran this search, and this took about 0.6 seconds. Now, in this demo, we're intentionally slowing things down, by the way, because this is not running on Edge itself. So we're trying to do artificial slowdown just to kind of simulate what it would be like if it was running at different processing speeds. So the latency, you can kind of take this latency with a grain of salt. But when we actually talk about the performance metrics that we got as a result of our full experiments, those are more accurate because those ran in actual Jetson Nano device. Okay. So there's a really small data set, so the amount of memory used is only about 2 megabytes. Estimated recall is 0.9, which is nice. This is what we recall. High recall with decent speed. And these are the search results we actually got. So we searched for this within our data set. These are the 5 nearest search results we got back as our responses. And as you can see, they do tend to line up pretty well. Okay. Now, as we go down a little bit here, we can see where our 3, we can see that we actually to show its connections. well, this part here, we're supposed to get a visualization that shows the actual nearest neighbors in vector space connected to our star, but it's not popping up. So it would be this part. It's too small. There it is. Okay. So these data points are a bit too small. Let's switch over to set of nodes. Some terms we can use. Just give me a second.
Yeah, Sergio, your audio seems to be going in and out. I don't know if you could adjust your microphone a bit.
Okay, let me see.
Yeah, that's much better.
Okay, great. Yeah, I know it from. Okay, great.
Thanks.
All right, nice. So yeah, just to kind of recap in case that what I said before wasn't heard, we're actually demonstrating some semantic search here. So we're going to be searching for this term in our data set. In a real situation, a real life example, this data set would be a lot bigger. This is only about it's 102 items, so it's pretty small. In a real situation, we have much bigger data set. The test data set we actually used for this was about 1 million records at its peak. So it's usually a lot bigger. But just for demo purposes, we're gonna keep it small, right? So we got pretty good search time. Again, we are artificially slowing this down. If this was running on like my machine, which it is running on right now, it would be very quick. But the idea is we're trying to simulate what it looks like if it was running on an edge device itself. When we actually talk about the performance metrics from the experiments ran when doing the actual research, we'll see what those look like when it was running on an actual device, which are, because it was running on the actual hardware, those are like very solid numbers that we can go by. Right? We got really good recall, and this is only 2.5 megabytes because, well, it's a very small data set, so there's nothing, we don't expect like huge results there. So we can actually see in our data set, we can actually see these were the different data points, where each one of these data points represents a specific piece of text. And when we entered this new query, it returned the 5 nearest neighbors to that query. That is the 5 pieces of text that are most similar to this text entered here, right? And we can see we have wireless charging pad, multiple device support, portable ultrasound device for at-home pregnancy monitoring, gesture control armband for presentations and device control, etc. And when we actually take a look down here, we can see the actual visual representation of the search taking place. Now, again, if you're really familiar with vector search, this is not too exciting. This is just how any vector search system works. But the idea is that we want to show that, well, the idea here is I want to get the point across to persons who may not be familiar with vector search, as well as to kind of point out, which we'll do as we head down further, why this method works really well for edge devices. Okay. So as we come down here, we just have a little section. This section kind of plays along with the previous slides that we had, where we actually just going to go over the span algorithm and how it works with some better visualizations here, right? So we talked about span pretty generally before. It's essentially a library that allows us to do hybrid. It essentially allows us to do hybrid search with disk-based storage and in-memory storage using for vector search. Right? We can go over it step by step how it works. So the first step is that we have these outer nodes here, these little circles. Each one of these represents a cluster of our data, So at the leaf level of the tree, at the bottom level, each one of those represents a cluster of data or partition. And as we look here, we can see these are what the partitions would look like. So each cluster represents one partition of data. When you get a new vector, the first thing you do is you identify which partition that data is closest to. So in this case, we have 4 partitions here. And then you essentially look, to determine how close something is to a partition, what we're going to do is we're actually going to identify the centroid, which centroid it's closest to. So and the centroids are the only thing that we store in memory. So if we come over here, we can see we have 4 centroids, and we just identified which one of these our query data point is closest to. In this case, it's going to be centroid 3, I think. Yeah, it will be centroid 3. And then from there, once we identify which centroid we're closest to, only at that point will we load the contents of partition 3 into memory and do a deeper level search. So here, we can identify that we are pulling everything into centroid 3, that we are close to centroid 3. Then we pull partition 3 into our memory, and then we're actually going to do a deep level search here. And the idea is that by doing this process, assuming that the index was constructed properly, we can guarantee that we get really good recall, really good performance overall, while maintaining a really low memory footprint. So here is where we have a brief like visual to show how this will compare to like a traditional vector search. So traditional vector search is usually the entire data set is pulled into memory. So you can see it's like 100% of the index is in memory at any given time. Whilst with our system, it's only going to be like a very small proportion that can be pulled into memory at any given point. And then so as we come down here, I'm trying to get this to fit on screen. As we come down here, we can see there's another visual that we have just to show essentially how this works a little bit more. So initially, we have 5 megabytes in memory. That's just our query, and then as we head across, we load all of our what we call our cluster heads, which are the centroids of each partition, and then our memory footprint goes up to about 50 megabytes. When we've identified, once we've identified that we are going to be searching for within a particular partition, we load the contents of that partition. The actual loading process will have some overhead, so that's why it's going to be 150 megabytes. After the loading is done, we're saying we have approximately 100 megabytes, and then we do the search within this criteria. So at any given point, our peak memory usage is going to be significantly lower than for a traditional vector search system. Just have a general run through of that system here. Okay, so that's the technical, that's a high level technical view of what we're doing and why this works a little bit better. There are a lot of really low level considerations that had to be made, like in terms of just getting this to run on our devices, and like making sure and making sure the actual code is efficient, but we're not gonna go to that level for this talk. Okay, now the idea here, when we actually ran this experiment, we ran it on NVIDIA Jetson Nano with 2 gigabytes of RAM, and we actually utilized only CPU evaluation. Now, the reason for that is just because when we're running this, the idea is that even though the Jetson series of devices tend to have GPU support, not all edge devices, I think not most edge devices have like dedicated GPUs. So we want to just see like how would it perform with CPU only, and then maybe down the line we'll integrate GPU support to see if it enhances performance greatly, and then you can have some devices, some applications specifically designed for devices with that type of architecture. Right? The dataset we utilized for the evaluation was the GIST-1M dataset. It's a dataset with 1 million records, some high dimensional image descriptors. And essentially what we did was we cut that dataset down to 10K to 1 million entries. So it wasn't 1 million all the time. We need to see how well it performed at various index sizes to see how that would affect performance. And we also cut the dimensionality of the data down from 64 to ranges between 64 and 960 dimensions. And again, this is just to see how dimensionality itself would affect performance. Because if we test the search and it works really well for 128 dimensions, that's great. 384 dimensions, that's great. But we want to see how dimensionality scales our search speed, which it usually will make it take a lot longer time. Right? The metrics we looked at were latency, recall, and memory usage, peak memory usage. So not just we didn't look at the average for the entire round. We just looked at how much did you need at most throughout your entire run. And each measure was done on a single query basis. So no bulk query processing here. The idea is that on edge devices, you're usually going to be running these. You're usually going to be running these in like real-time environments, and you're not going to be sending bulk workloads. Okay, so recall is just to see how many items you correctly identified as being the most relevant items to a particular query. Okay, so our results. So our results, we actually end up with an average latency of 0.085 seconds, a peak latency of 0.93 seconds. Now, this peak latency was with maximum dataset size, maximum dimensionality size. So, 1 million records, 960 dimensions. So on a pretty small device, which is usually unlikely to have a data set of that size just loaded onto it. So I think 0.93 seconds was pretty good, though I think we could still get it better. Our recall was 91.59%, which was very, very, very good. Our peak memory usage was 873 megabytes with an average usage of 313 megabytes. Again, the 873 megabytes was essentially for biggest data set size. That is 1 million records, 960 dimensions. So again, very, very big data set, very high dimensionality, even on a pretty small device. So this stayed well below our threshold. So the Jetson Nano that we used had 2 gigs of RAM available, and we essentially allocated 1 gig to be the cutoff point, where we decided that it would be unfeasible to run this situation. So we set a limit as 1 gig, and we stayed within that limit pretty comfortably for most of our tests. So overall, we determined that we got really good latency, pretty high recall, and very good resource utilization. So we were very happy with the results. So this is usually where I would have dropped the vector search demo, but we decided to do that a little earlier because it kind of leaned into the explanation of the indexing module. Okay. Now, for what we plan to do in the future. So that's what we worked on. I'm pretty happy with the results. And well, the work was published at a conference in December. When it was presented there, the persons there seemed pretty impressed with the results as well. But for future work, what we want to do is we want to maybe implement some GPU utilization. So like I said, we did this based on CPU utilization only. Maybe GPU utilization on these edge devices would be a better use, would make the performance significantly better. I mean, it would make it significantly faster, just to see how we could really take advantage of that. Some more robust performance profiling. So our main concern here was memory utilization, but CPU utilization is really important. And the main reason we didn't do that is just because of our lack of time overall. And then we want to look at both distributed cloud architecture as well as maybe a heterogeneous environment. That is, can we run this on multiple devices with different architectures and have them operate together in like a single network and have them cleanly do this vector search in an efficient way? I think that would be very nice, and that's what we're currently looking at when looking for like a publication for this. Okay, with that's it from me. Does anyone have any questions?